So today we're going to make progress from where we stopped yesterday. Yesterday we started talking about uniform accelerated motion, and we showed what uniform accelerated motion looks like using a velocity time graph. That it on a velocity time graph, uniform accelerated motion is actually a straight line. That's what we showed yesterday. So we had a velocity time graph like this. So we showed that this straight line, with a straight line on a velocity time graph, it represents uniform accelerated motion. What we learned yesterday was that from the slope or the gradient of this straight line, this velocity time graph, when we worked out the gradient, we found a quantity which had units of acceleration, and we concluded that that slope or gradient was equal to the acceleration of the object which was moving. From the area under this graph, we worked out the area under this graph, and we found out that the area under the graph was 140 meters, and that led us to the conclusion that the area under the velocity time graph represents the displacement or the distance covered. So in this lesson, instead of working with graphs, we are going to come up with some equations which look like mathematical things, but they are not mathematics, they're physics things, which we can use to describe what's happening when you have uniform accelerated motion, and also which can help us to predict and analyze what's happening. So we're going to come up with 5 equations during the course of this lecture, and you're going to see how to use those equations to actually solve an example of uniform accelerated motion, which happens when you drop something or you throw something upwards. So, our starting point is the fact that the acceleration of a velocity time graph, the acceleration of an object is equal to the slope of the velocity time graph. This is where we're going to start from. So we start with the velocity time graph, and that's what we use. That's why it's very, very important. So we have the start point, the distance covered. You're going to represent the distance covered as S. We're going to represent the time taken to cover some particular distance as t. The initial velocity at time t equals to 0 will be u. The final velocity at t is going to be equals to v. So this u and v are values of instantaneous velocity, and the acceleration itself is going to be a. So how do we define acceleration? So the acceleration, according to this slope of a velocity time graph, and how do we define the slope? In this case, the slope is going to be equal to the change in the velocity divided by the time taken to carry out the change. So that's going to be equal to the change in the velocity divided by the time taken. The change in the velocity itself depends on what the initial velocity was and what the final velocity is. So this change in velocity is a difference between the final velocity, so it's v minus u, the final velocity, and the initial velocity. That's what the change in velocity is. So we've got some people, need to admit. So this is this bit on top, the change in the velocity. Then, which represents, we start here. So when you start from this point, this velocity here is u equals to 0. That's our initial velocity. And when you end at that point, our final velocity v is equals to 28 meters per second. So the change in velocity is equals to the final velocity, which is 28 meters per second, minus the initial velocity, which is 0 meters per second. So the change in velocity is equals to 28 meters per second. So that's what that is. That's how you work out the change. Then you divide by how much time it took to carry out the change. That is 10 seconds. So basically that's what you do if you want to work out the change in velocity, like that. This change in velocity, delta v, change in velocity, can be rewritten as like this. V, which is the final instantaneous velocity, minus the initial instantaneous velocity, so v minus u. V is the final velocity after time t, then u is the initial velocity when we just start measuring the time. So we have acceleration is equal to v minus u divided by time. So here our a is acceleration in meters per second squared, v is the final velocity, u is the initial velocity, t is the time taken. If we multiply on both sides by t, so we multiply this side on the left hand side by t, we multiply on the right hand side, on the left hand side this side by t, we multiply on the right hand side by t, what we get? So we multiply on both sides by t. So you multiply on both sides of equation 1 by t, what we get is this. AT is equals to v minus u. Then we add plus u on both sides. So when you add plus u on both sides, we end up with this. We end up with v is equals to u plus 80. This is what we end up with. V is equals to u plus 80. This is the first equation which we can use to describe or predict uniform accelerated motion. With this equation, equation 2 allows us to find what the final velocity is if we know the initial velocity and the acceleration and also the time taken. This whole thing depends on whether there is acceleration. So if there is no acceleration, that means that if the velocity is not changing, in other words, if the velocity is constant, it remains the same, then in that case, a, which is the acceleration, is equals to 0. If the acceleration is equals to 0 multiplied by whatever amount of time takes place, the initial velocity will always be equal to the final velocity. So in this case, without acceleration, v, which is the final velocity, is always equal to the initial velocity. Nothing interesting is happening. So the only interesting things only happen if there is acceleration. Are we clear? So the first equation, which is equation 2, is v is equals to u plus 80. This equation gives us a way of predicting what the final velocity is going to be if we know the initial velocity and we know the acceleration and also how much time has taken place. Are we clear? With equation 2.
Yes,
Okay. Next, so this is what we have obtained from the slope. Okay, this is what we have obtained from the slope. The next thing we want to concentrate on is the area under the graph. Now the area under the graph, under the velocity time graph, is equal to the displacement. And for you to find the displacement, you need to know what the average velocity is. For you to find the displacement, you need to know what the average velocity is. Because once you know what the average velocity is, the average velocity multiplied by the time, so average velocity multiplied by time gives you displacement. So if the initial velocity we know is u, the final velocity is v, using these two values, the initial velocity and the final velocity, we can use this expression to get our average velocity. So our average velocity, v bar, is equals to half u plus 80. That is our average velocity. With this average velocity, if we multiply the average velocity, v bar, times the time it has taken for this object to move, what we get is the displacement. So we get displacement from average velocity. Average velocity is important in this case. So the average velocity, which is equals to half u plus v, we multiply the average velocity times the time it has taken the object to move. So in this case, our average velocity, our initial velocity is 0. Our final velocity is 28. So 0 plus 28 is 28 meters per second squared divided by 2. In this case, our average velocity is 14 meters per second. This 14 meters per second, which we're going to put here, multiplied by the time, 10 seconds, that gives us 14 meters per second times 10 seconds. That gives us a distance of 140 meters, which is the distance we found yesterday. So as much as this looks different, It is actually the same thing. Are we clear?
Yes.
Yes. So the displacement,
Yes, sir.
which is the distance which has been moved by an object in a particular direction, is equal to the average velocity multiplied by the time taken for that object to move. However, remember that in equation 3 here, we know what average velocity is. Average velocity is equal to half the initial velocity plus the final velocity. So we substitute for the average velocity in this expression. So we end up having displacement s is equal to half u plus v multiplied by t. Then we multiply and divide. So we multiply by t throughout, and this whole thing when you divide by multiply by half, so we end up with s is equal to vt. So if you multiply this times this, that's going to be vt. This multiplied by that, that's going to give you ut. So you're going to end up with s is equal to vt plus ut divided by half here. Now remember that this v, we have already found what v is. V is equal to u plus at. That is equation number 2. So we substitute for v in this expression of s. S is equal to vt plus ut divided by 2. So we substitute for v. When we do that, we end up with s is equal to, this is our substitution, u plus at, then multiplied by t plus ut divided by 2. Then we multiply by t throughout. We end up with s is equal to ut plus 80 squared plus ut divided by 2. There is ut this side, there is ut this side. So we have got 2 ut's. So when you add them, we end up with s is equal to 2 ut plus 80 squared. This whole thing divided by 2. So if you divide by 2 throughout, you end up with s is equal to ut plus half 80 squared. This is another important equation. So now we have got 2 equations. We have this one. Actually, you have got a couple of important equations. You have got this one. V is equal to u plus 80 squared. Then we have this one, which connects the distance or the displacement with the initial velocity and the final velocity and the time. Then we have this expression s is equal to ut plus half 80 squared. This one allows us to predict what the displacement is we predict what the displacement is or the distance is when we know what the initial velocity is. Then we multiply the initial velocity by the time plus half 80 squared. Again, if there is no change in acceleration, so if there is no acceleration, so if there is no change in velocity, then the acceleration is going to be equal to 0. When acceleration becomes equal to 0, this whole bit becomes equal to 0 because you're going to have half times 0 times t squared. So the only thing you're going to be left with is this. S is equal to u plus t. So if you know the initial velocity, then you know how much time has taken place. You can always predict the distance if there is no acceleration. But in this case, because there is acceleration, there is an additional part. This first part is when there is no acceleration. Then when there is acceleration, there is an additional part you need to add. This half 80 squared. Is that clear?
Yes, very clear.
Yes. We are trying to show you how you come up with these equations. You will not be asked to come up with these equations. In fact, we are going to give you these equations, but we want to show you this is how you come up with this equation, and this is what it's used for, and these are the things you can use, basically use the equation for. Okay, so this is another equation here. Next thing we're going to do is from equation number 1, this one, a is equal to v minus u divided by t. We are going to rewrite this equation number 1 by making t the subject of the formula, so that we end up with t is equal to v minus u divided by a. Like this. T is equal to v minus u divided by a. Why are we trying to do this? It is because we want to substitute for this t in this equation. We want to substitute for t. So where there is t here, we want to replace the t with v minus u divided by a. Here where there is t squared, we want to replace with v minus u divided by a. So when we do that, this is what we end up with. We end up with a is equal to u. In place of this t, we put in v minus u divided by a, then plus half a. Again, in place of this t, we put in v minus u divided by a. Then we multiply. So u multiplied by v is uv. Then minus u multiplied by u is u squared here. Then the whole thing divided by a. Then plus half a. Then v minus u is squared. This is what we have here. V minus u squared. Then at the bottom there we've got an a. So that a is squared. This a is squared. So we end up with that. So here you end up with s is equal to uv minus u squared divided by a plus half a. Then you've got this guy squared. Then there's an a squared here at the bottom here. So you've got an a here and there's an a squared there. So one of them cancels out. So you end up with, and you expand this. So you end up with s is equal to uv minus u squared divided by a plus u v minus u, then at the bottom, because you've cancelled out one of the a's, then you multiply this 2 times the a, you end up with 2a. Okay. Then next you expand this thing inside here. So you end up with v multiplied by v, that's v squared, then v multiplied by minus u, that is minus uv, which is, so you would v squared here, then minus uv here, then minus u multiplied by v, you end up with another minus uv here. Then you have minus u multiplied by minus u, you end up with plus u squared there. So we have s is equal to uv minus u squared over a plus this whole expression here, then divided by 2a. Then you have got this minus uv minus uv. So basically that ends up becoming minus 2uv. So you end up having 2uv. And you have a here, you with this a and that. So the common denominator is going to be 2a. So when this a gets into this 2a, you're going to have 2, and that 2 is going to multiply these two guys. So you're going to have 2 uv minus u squared, which is what you have here, 2 uv minus u squared, then plus this guy uv squared, then minus this and that is minus 2uv, then plus u squared, which is this. So the expansion and simplification of things on top and the bottom is what you have up there. This is 2uv, there is minus 2uv. So this and this bit, they cancel each other out. 2uv minus uv minus 2uv, this and this, they go. Then you've got this guy here minus 2u squared, then plus u squared. Minus 2u squared plus u squared is going to give you minus u squared. So at the end we end up having v squared, which is this one, minus u squared divided by 2a. We multiply on both sides by 2a. When you do that, you end up with 2as is equals to v squared minus u squared. Then you take this u squared to the other side. When you do that, you end up having v squared is equals to u squared plus 2as. So this is another equation which we need, which we will use to describe uniform accelerated motion. Again, if there is no acceleration, nothing happens. If acceleration is equal to 0, then you end up having only v squared is equal to u squared. So basically, the initial velocity is equal to the final velocity. The velocity doesn't change. So that's not something which is interesting. That is basically an example of an object which is moving at constant speed. We are not really interested in that. So the equations we have come up with, there is this first one, A is equal to V minus ut. That's for how we define what the acceleration is. From this equation, we came up with this. V is equal to u plus at. Then later on, from the definition of average velocity, which is equal to half u plus v, we worked out what the displacement is going to be. S is going to be the average velocity multiplied by the time, and this gave us this expression. It's a very, very important, quick way of finding out what the displacement is. So if you know the initial velocity, you know the final velocity, you know the initial velocity, you add them, you divide them by half, you multiply by t, you get yourself the displacement. So we came up with this, then we did some substitution, then we came up with another way of working out what the displacement is going to be, which is this. S is equal to ut plus half at squared. We did some substitution. In place of t, we replaced with v minus u divided by a, and we ended up with this. V squared is equal to u squared plus 2as. So these are the equations we are going to be using to describe uniform accelerated motion. In all these equations, it is assumed that the acceleration will not change. The acceleration will remain the same. That's why it's called uniform accelerated motion. Are we clear?
Yes, sir.
Any questions?
But I need some more explanation on how the S came.
How the what?
How the S, the so-called the displacement, came into the equations.
The displacement.
Yes, sir.
This.
Yes, the same one.
This displacement, we took this form because if you look at the way it is, from what we worked out yesterday, where the initial velocity, when you look at this graph, yesterday we came to the conclusion that the area under this graph is equal to the displacement, and we worked out an area of 140 meters. The area under the velocity time graph. Okay? However, when you try to work it out like that, just making a direct substitution like that, things a bit become more complicated. So we took another approach, and while also at the same time showing that this approach is equivalent to what we did yesterday by using what is known as average velocity. I think we have introduced this quantity before, average velocity. So the average velocity is also equals to half u plus v. So in our case, our initial velocity was 0 meters per second. Our final velocity was 28 meters per second. So when we do that, 0 meters per second squared plus 28 meters per second, that gives us 28 meters per second. Then we divide by half, we get 14 meters per second. That 14 meters per second is our average velocity. Okay? Which is what we have here. Our average velocity, if we multiply the average velocity times the time, which is the 10 seconds, we still get back 140 meters. So by doing this, I have shown that this expression S is equal to average velocity multiplied by the time is equivalent to what we did yesterday, where we worked out the area under the graph. So this is just another way of doing it. The two expressions are the same. Remember, average velocity is equals to the total displacement covered divided by the time taken. So what we have just done here is actually we have just made the displacement the subject of the formula. Are we clear?
Yes, sir. Say now.
Yes, we have just made the displacement the subject of the formula from the definition of average velocity. Average velocity is equal to the total displacement divided by the time. So when we make the displacement the subject of the formula, we end up with S is equal to Vt, V bar minus T. Then now that we have this V bar, which has been worked out like this, then we substitute it here, then we proceed. Any other question? Is there another question? Okay. Now, an example of uniform accelerated motion is a change in velocity which occurs under the influence of something called gravity. Gravity is why things fall. Okay? Because the Earth, any object with a huge amount of mass, like the Earth, has a tendency to behave like a magnet. It pulls things to itself. That's why things fall on the ground, towards the ground. Okay? If you are holding something, then you let go, it always falls towards the ground. Water, if you're washing your clothes, then they are wet, then the water is going to drop towards the ground because the Earth always pulls things. If you've got a waterfall always goes down because the water is being pulled. So everything on Earth is being pulled towards the Earth. That's what gravity is. When something is being pulled towards the Earth, towards the surface of the Earth, it tends to change its velocity. Okay? If you are holding something in your hand, the velocity of that thing you're holding in your hand is 0 meters per second. When you let go of that particular object you're holding, the velocity of that object will not stay the same. The velocity will change. In fact, the velocity will increase as that particular object goes towards or approaches the surface of the Earth. The acceleration with which the velocity of any object, in this case, in terms of gravity, increases is by 9.8 meters per second. Every second. So with gravity on Earth, not everywhere else in the universe, but on Earth, the velocity is going to increase by 9.8 meters per second. On the other hand, if you throw something away from the surface of the Earth, then the velocity of that particular thing is going to reduce until it becomes zero. When it becomes zero, then we conclude that that particular object has reached maximum height. So when things are falling towards the surface of the Earth, their speed tends to increase. And that speed tends to increase by 9.8 meters per second every second. When things are going away from the surface of the Earth, their speed tends to reduce, and it reduces by 9.8 meters per second. So they slow down until they come to a stop, then again they fall towards the surface of the Earth where the velocity begins to increase. So if you drop an object from a height, okay, it accelerates towards the surface of the Earth at a steady 9.8 meters per second every second. If when you're dropping it, let's say you don't kind of throw it, you just let it go. So in that case, your initial velocity of the object is going to be 0 meters per second. Once you release it, after that, the velocity is going to increase by 9.8 meters per second every second. This thing has been mistimed. So it's going to increase by 9.8 meters per second every second. So it means that the acceleration is this much. If the object is going away from the surface of the Earth, going up, the other thing happens. The velocity will reduce by 9.8 meters per per second until the velocity becomes 0. When the velocity becomes 0, then we conclude that the object has reached its maximum height. So whatever the velocity was, it will keep on reducing by 9.8 meters per second until it becomes 0. Okay, so in that case, we conclude that since the object is slowing down, the acceleration of the object is minus 9.8 meters per second. Whether the object is going up or down, the size of the acceleration is the same. Are we clear? Whether the object is going up or down, the size of the acceleration is the same. It's always 9.8 meters per second every second. The difference is that when an object is going towards the surface of the earth, it increases in speed. It gains speed. When it's moving away from the surface of the earth, it reduces in speed. So the difference is the negative sign. When you're moving towards the surface of the earth, your acceleration has got a positive sign. When you're moving away from the surface of the earth, your acceleration has got a negative sign. That is why acceleration is a vector. The negative sign shows direction and what's happening. If you move towards the surface of the earth, plus 9.8 meters per second. If you move away from the surface of the earth, minus 9.8 meters per second. Are we clear? Yeah. So under the influence of gravity, we have a specific value on Earth for acceleration. Under the influence of gravity, we have a specific value on Earth for acceleration, and that is this: 9.8 meters per second. So our equations, where there is A, if you just put G there, so you end up with G is equals to V minus U divided by T. This other one, V is equals to U plus GT. This, where there is G, that's where there was A. This other one, S is equals to half U plus AT. This other one, S is equals to UT plus half GT squared. This other one is equals to V squared is equals to U squared plus 2 GAs. We are able to predict, not fairly exact, but we can make very good predictions with these same formulas which we have by just changing the value of the acceleration 9.8 meters per second. So you can predict how fast something is going to fall, what's going to be the velocity of this particular thing after a certain amount of time, how much distance it would have covered after a certain amount of time, and stuff like that. Okay, so during the upward motion of a body, the acceleration due to gravity is negative, minus 9.8 meters per second. On the other hand, the acceleration due to gravity is plus 9.8 meters per second when a body is moving towards the surface of the earth. Are we clear? Any questions?
No questions. It's clear.
All right. So I'm going to look at an example. In this case, yes. What's the question? Okay. So we're going to look at an example. A bullet from a rifle shot upwards has a muzzle velocity of 550 meters per second. Calculate the time it takes the bullet to reach its maximum height. B, the maximum height reached by the bullet. C, the total time of flight of the bullet. D, the velocity with which the bullet strikes the ground. So here we have something which is, if you shoot a gun upwards, clearly the bullet is moving upwards, so it's moving away from the surface of the earth. Therefore, if it's moving away from the surface of the earth, its initial velocity was 550 meters per second. When it reaches maximum height, for something to reach maximum height, its velocity must have become 0. So the velocity of this bullet actually changes. It reduces until it becomes 0. Once the velocity of the bullet has become 0, then we convince ourselves that this thing has reached maximum height. If the velocity is not equal to 0, then we say it hasn't yet reached maximum height. That is our definition of what maximum height is. When the velocity of the bullet will become 0. So we know the initial velocity of the bullet, 550 meters per second. We also know that at maximum height, the final velocity of the bullet is going to be 0 meters per second. We also know that the bullet is moving away from the surface of the earth. It's going up. So in that case, our acceleration is equal to minus 9.8 meters per second. With this information, we can find out how much time it takes the bullet to reach maximum height. And we can do that using this formula. V is equal to U plus GT, where U is our 550 meters per second plus our G, which is minus 9.8 meters per second because the bullet is moving away from the surface of the earth. Then the T is the time we're looking for. Then at maximum height, the velocity of the bullet is 0 meters per second. When we substitute these values, final velocity is 0 meters per second, initial velocity 550 meters per second plus G minus 9.8 meters per second squared multiplied by the T, which is the rise time. Then we can work out how much the rise time is. We drop off the units, so we end up with 0 equals 550 plus minus 9.8 T. And this gives us 0 equals 550 minus 9.8 T. Then you take the 9.8 minus 9.8 to the other side, you have 9.8 T rise equals to 550. Then you divide this, T rise equals to 550 divided by 9.8. Then you end up with T rise equals to 560.1 seconds. So it takes 56.1 seconds to reach maximum height, which is less than a minute. Is this clear?
Yes, sir.
Yeah, so we use this expression here. You just have to choose, when you're trying to work out problems of uniform accelerated motion, choose a formula which is easy. Okay. Next, we want to find the maximum height reached by the bullet. We know that the initial velocity of the bullet is 550. We can use this expression. S is equal to ut plus half at squared. Ag squared. So in this case, our initial velocity is 550. Then the time it takes the bullet to reach maximum height is this one, 56.1 seconds. Then plus half, then G, the acceleration due to gravity, it's moving away from the surface of the earth. Then of course there's the T there. So we basically, that's our way we're going to find the maximum height. So we substitute for 550 meters per second, then the time to reach maximum height, the rise time, 56.1 seconds plus half, then minus 9.8 meters per second squared, then 56.1 seconds squared. Then we proceed to drop off these units to make things life a bit easy for ourselves. So we have 550, then 56.1 minus half, 9.8, then 56.1 seconds squared. We carry out this multiplication, you end up with this 15,431 meters per second, meters, which is approximately equals to 15.431 kilometers. So that's basically the maximum height to which the bullet rises to. Of course, there's another way we could do this. Since we now know how much time it takes the bullet to rise. With that time, 56.1, we know the initial velocity. The initial velocity is 550 meters per second. We know the final velocity of the bullet is 0 meters per second. We can use this. Our initial is 550 plus our final velocity is 0 meters per second. So that is 550 plus 0 meters per second is 550. Then divide by 2, that gives us, I think, 225. Then 225 times 56.1, that should give us the same thing. I can try to do a quick calculation on my phone and confirm if the result is the same. So initial is 550, then final is 0, then you divide by 2. So that, yes, so that gives us the average velocity is 275 meters per second. Then you multiply that by 56.1, and we get the same thing. So when you use this formula, what you get is actually 15,427.5. The other formula has given us how much? We have 15,434. The other one is 15,427. The difference, they are not exact, but they're very, very close. And what we are doing in physics is predicting. So the predictions with those two formulas, while they are not exactly the same, but they're very, very close and they are acceptable. So you can say, okay, fine, the maximum height approximately is going to be 15,430. Are we clear? Are we clear? Okay, no questions. Next, the total time of flight of the bullet. The bullet takes, from what you have found the rise time, the bullet takes 56.1 seconds to go up. It also takes the same amount of time to come down, as we are going to show. For the bullet to fall from maximum height, it takes the same amount of time. So at maximum height, the initial velocity is 0 meters per second squared. That's the initial velocity at maximum height, 0 meters per second squared. And when it falls, it's going to cover the same amount of distance. The distance to maximum height is the same distance through which the bullet is going to fall through. The difference here is that the bullet is going to be moving towards the surface of the earth. In that case, the acceleration is going to be 9.8 meters per second. So we use the same equation, s is equal to ut plus half at squared, with a difference. We know the maximum height now. S max is known. We also know the initial velocity at maximum height. The initial velocity is 0 meters per second. We are looking for the time plus half gt squared. Since we are coming towards the surface of the earth, the g is 9.8 meters per second. So when you make the substitutions, for the height through which the bullet is going to fall is the same as the height through which it rose. That's 15,434 meters. Then multiplied by the initial velocity from maximum height, that is 0 meters per second, multiplied by the time of fall, then plus half the 9.8 meters per second squared, then time of fall squared. This, when you drop off the units, we have 15,434 equals to 0 multiplied by T4, then plus half 9.8 T squared 4. This 0 times T4 gives you 0. Then you would half multiplied by 9.8, which is this 0.5 times 9.8, you end up with 4.9. So 4.9 T squared 4 equals to this. Then you write it a bit the other way, you have 4.9 T4 squared equals to 15,434. You divide by 4.9 on both sides, you end up with T squared 4 is equals to 15,434 divided by 4.9, and you end up with this. Then you square root on both sides, you end up with T4, which is equals to 56.1 seconds. So it takes the bullet another 56.1 seconds to fall from maximum height. This T4, as you can see, 56.1 seconds, and T rise, 56.1 seconds. What you see here is that the time it takes the bullet to rise to maximum height and the time it takes the bullet to fall from there are the same. Okay. So the total time it has taken the bullet to go up and then come down is going to be the sum of T rise and T fall. So the flight time, T flight, is going to be equal to T rise plus T fall, which is going to be equals to 56.1 seconds plus 56.1 seconds, which gives us a flight time of 112.2 seconds. Are we clear?
Yes, sir, very clear.
Yeah. The one thing to note here, which is very, very important, is that the time it takes something to go up and the time it takes to come down is the same. If and only if the height through which the object is falling, the height through which the object rises, and the height through which the object falls are the same. So if the object goes up through a particular height, it takes a certain amount of time, then it falls through the same height, then the time to rise and the time to fall are going to be the same. And that time, a combination, the sum of the rise time and the fall time, that is what we refer to as the flight time. The duration of time for which the bullet has been flying in the air. The other thing which is of interest is the velocity with which the bullet is going to strike the ground. So when the bullet is at maximum height, we know that the velocity is equals to 0 meters per second. From maximum height, because the bullet is coming towards the earth, its velocity is going to increase at the rate of 9.8 meters per second squared. So from maximum height, as it comes down like that, the velocity of the bullet will increase. By how much? Well, we know how much time the bullet is going to take to fall. We know the fall time, 56.1 seconds. So we can predict with what velocity the bullet is going to strike the ground. So the final velocity v is going to be equal to the initial velocity plus gt. So the initial velocity at maximum height is 0 meters per second squared plus g, which is acceleration. Because the bullet is coming towards the surface of the earth, it means that the acceleration is positive, that's 9.8 meters per second squared, then plus t. This is the fall time. Like that. We drop off some units, we end up with v is equal to 0 plus 9.8, then 56.1, like that. You work out what this is, you end up with v is equal to 549.78. This 549.78 is basically approximately equals to 550 meters per second squared. So, this 550 meters per second squared is the same as the velocity with which the bullet left the gun. This muzzle velocity, 550 meters per second. So what does it show? It shows that if a bullet goes up or anything goes up, it takes a certain amount of time, then it comes down, it takes the same amount of time it took to go up. In that case, the velocity with which that particular object is going to hit the ground is the same as the velocity with which it was thrown up. Are we clear? The velocity with which an object strikes the ground is the same as the velocity with which that particular object went up. So there are a couple of things here. The rise time, if the distance through which the bullet rises and falls is the same, then the rise time and the fall time are going to be the same. But they are not the only things that are going to be the same. It also means that the velocity with which the object is fired from the gun and the velocity with which it hits the ground will be the same. Are we clear?
Yes, sir, very clear.
Yeah. So that's where the physics is. If the height is the same, then the time of flight and the fall time, the rise time and the fall time are the same. But also the final velocity, the strike velocity and the launch velocity will also be the same. Okay, any questions?
Yes, the question.
Yes.
So like when you know that the final velocity, the velocity that an object strikes the ground is just the same as the initial velocity, is it okay to conclude without solving that?
Only
You know that it's
if
just the same?
it is the same, only if the height through which this object has risen to and fallen is the same.
So it's okay to conclude without
I'm
solving.
saying only if. You have to give us a reason why they're the same. If you don't want to work out something, you want just to make a conclusion, then you have to give us a reason why this is so. So you tell us it is because the height through which the bullet goes and falls are the same. Therefore, you conclude that. You can try to show, or you can just conclude that they're the same. If you know this fact, then you can save yourself the trouble of solving. For example, in a quiz, if you are answering a quiz, then there is a situation like this. Someone throws a coin up with a certain amount of velocity. Then the coin comes down. Then we ask you, with what velocity is the coin going to strike the ground? You know, if it's going up a certain amount of height, then it's falling through the same height, then you know. Say it's the same. But there's a condition there. The height has to be the same. If the height is not the same, for example, if you shoot something up, then it falls on a mtenge or on a mountain, then it's not going to be the same strike velocity. Are we clear?
Yes, sir, very clear.
Okay. Any other question?
No.
Did I hear a no? Oh, there are no questions? Alright, if there are no questions, then we'll end here.
There's a question, sir.
Yes.
Ask.
What's the question? Okay, we'll stop sharing since the question is not forthcoming. And yeah, we'll stop here. So see you next week.